Hi everyone. If you like the way I teach and want me to be your teacher, the link to my engineering fundamental school is in the description below. Enjoy the video. In the last couple of videos, we've been discussing the moments of areas, particularly the first and second moment of areas. If we observe the first moment of area equation, what it's saying is that the moment produced by all the little areas is the same as the total area placed at a special distance away. That y bar is the y coordinate of the centroid, and the right-hand side of the relation is called q sub x, or the first moment of area about the x-axis. The second moment of area, I sub x, takes a similar form. If we write down the moment of area, y dA, and take another moment, y, we get y squared dA. Again, this is called the second moment of area, or the area moment of inertia about the x-axis. On screen is an example of a centroid and moment of inertia table. For an area, a triangular area with a base b and a height h, if we wanted to find the moment of inertia, or if we wanted to find the centroid of this body, we'd have to perform a double integration if we weren't given this table. Now we could perform double integration, or we can also reduce the problem to a single integration, which we can add up all these thin strips and get our solution. That's what this video is going to be on. It's using calculus to solve problems of moment of inertia and also centroid. Shown here is a Cartesian plane with the function y equals to mx. Of course, we can find m using the relationship of what a slope is. We know what the function is. Now, if we wanted to find the y coordinate of the centroid, what would we have to do? We would have to choose a strip. We would have to find the dimensions of the strip, which is y dx. Its height is y and its width is dx. But the moment produced about the x-axis from the strip, the moment arm is y over 2, not y. I would recommend you do not choose this area. If you choose it like this, the process becomes more difficult when we move on to moment of inertia, which involves a y squared, and this process would not work for. Instead, let's choose a horizontal strip. This horizontal strip would have a height dy and a width which is equal to b minus x. Why is it beneficial to take the moment in this fashion? All of the particles which make up this strip all have exactly the same distance from the x-axis, or exactly the same moment arm. So we can correctly integrate here and leave that y as in y and not have to modify it to like y over 2, as we did in the last case. If we wanted to carry out this integration, we could, and the steps are shown here. As we can see here, the y coordinate does match. What if we wanted to find the x coordinate of the centroid? We would choose a differential area where if we took the moment about the y-axis, we would have a constant x distance. What does that mean? We need to choose a vertical strip because a vertical strip has a constant x coordinate. Its height is y, its width is dx, and we can substitute in the relation for y. We can carry through the integration as shown on screen. You can see this x bar matches our x bar in the table, so we are correct. What we're going to do next is verify the moment of inertias of this table. We'll start off with the moment of inertia about the x-axis. Again, we're going to use a horizontal strip with a constant y coordinate away because we want the moment arm to be the same for every particle in that strip. An easy way to remember this is if the moment of inertia is dealing with y's, we want to use a dy. If we're using a dy, our strip must be horizontal. Again, this is the same differential area that we previously used, so let's carry through the calculation. This matches our value in the table. Let's move on to IY, or the moment of inertia about the y-axis, where we're using x distances and we want a constant moment arm. If we use a vertical strip, its height would be y, its width is dx. We can carry through the integration as follows. And we can see we have matched what was in the table, so we're correct. Let's go ahead and move to our example. This example is going to be complete. We're going to find the entire centroid, the x bar and y bar, the moment of inertia about the x and y axis, and also the moment of inertia about the centroidal x and y axis of the following figure. This figure is an area bounded by two curves. It's the hashed area shown on screen. And our goal is to find all these quantities shown on screen. If we wanted to start off, how could we find the x-coordinate of the centroid? Of course, we're going to use the centroid equation, and we're going to think, which differential area should we use? Of course, we want that constant moment arm, or if we think, what's under the integral? The x value is on the integral. We want a dx, meaning we want a vertical strip. What is its height? Its height would be the top function minus the bottom function, or root 2x minus x. The only thing we don't know is the bound of integration, or the area. So right now we're finding the intersection point. The intersection point can be found by equating the two equations, and we see that y equal to 2 is an intersection point. We can also integrate under these curves and be able to find the bounded area, which we're going to need for our x bar calculation, and most of our other calculations as well. We can see that that area is going to be equal to 2/3, and that's an important quantity, so we'll note it down. Let's go ahead and perform our integration. That first term is a 1 over area term, or the reciprocal of the area. We get an x bar value of 4/5. Let's go ahead and compute y bar. Of course, y bar is involving a y coordinate. We're going to want to use a differential y element, or a horizontal strip. The width of this strip is going to be the y equal to x function minus the left side function, which is y squared is equal to 2x. We take the difference of those two functions, we get the following differential area, and we can carry through the integration as shown on screen. The next thing we're going to want to do is find the moment of inertia of the y-axis. Of course, we can use the same differential area that we just used for the above calculation of x bar. We see an x under the integrand, so of course we're going to be using that same differential area involving x's. Let's carry through the integration, and we find the following answer. Let's go ahead and move on to the moment of inertia about the x-axis. We can use the differential area for y bar here. Let's carry through the integration and find our final answer for Ix. Lastly, if we want to be able to find the centroidal moment of inertia, we're going to have to think, is there a relationship between the centroidal moment of inertia and a moment of inertia about a parallel axis? Yes, we reviewed that in the last video. If you need a quick review of the parallel axis theorem, please watch my video on the parallel axis theorem. For now, we'll write down the equation and we'll go ahead and use it. The moment of inertia about any axis is equal to the moment of inertia about a centroidal axis plus the area times the distance between those two parallel axes squared. If we're looking at the x moment of inertia, what would that distance be? That distance is going to be the y bar value, as shown on screen. If we substitute in the equation, we get that IXC is 2/15. What about the y? What about the y centroidal moment of inertia? We can use the same relation, except that distance is going to be the x bar this time. We'll get an IYC value of 76 over 525. If this video was helpful for you, please like and subscribe, as it really helps me out a lot. Keep learning and keep working hard. Goodbye.